We're going to begin with a review of excircles. To skip this and go straight to the solution, look for a link in the video description. If we're given some triangle ABC, we can find one excircle, which we'll call excircle A. It'll be tangent to side BC, and we'll extend these other two sides AB and AC. So this circle will also be tangent to these sides. So it might look something like this. We'll call the center of this circle IA, and we'll let T be the tangent point on side BC, and the other two tangent points are X and Y. So we have right angles here at X and at Y. We're going to find the area of triangle ABC in terms of the radius of this X circle, which I'm calling RA. To do this, we'll first find the area of the quadrilateral A, X, IA, and Y, and then we'll subtract the area of the pentagon B, X, IA, Y, and C, leaving behind this triangle ABC. Let's start with the area of this quadrilateral. I'll connect the points A down here to IA. So this will be the sum of the areas of triangles AXIA and AYIA. X and Y are both tangent points, so we have right angles here. So we'll find the area in the usual way, 1/2 base times height, where the height is the radius of our X circle. And then I'll factor out 1/2 and RA. Since X, Y, and T are all tangent points to our X circle, we have this distance from B to X is going to be the same as the distance from B to T. And likewise, the distance from C to Y is the same as the distance from C to T. The perimeter of triangle ABC, we can write it as the sum of the distances from A to B, B to T, and then A to C plus C to T. Now we'll do these substitutions, substituting BX for BT and CY for CT. Since A, B, and X are all collinear, this is the distance from A to X, and these two add up to the distance from A to Y. The sum of these two lengths is what we had in our expression for the area of this quadrilateral. I'll substitute the perimeter of our triangle, and half of the perimeter, we can call that the semi-perimeter. Now let's find the area of this pentagon. We'll find this by dividing this pentagon into 4 triangles, starting with the left, BXIA, BTIA, and then here on the right, CTIA and CYIA. We can see that these first 2 triangles are congruent to each other by hypotenuse leg. The legs are congruent and they share this hypotenuse from B to IA. So I'll just write this as 2 times the area of our first triangle. And these last 2 triangles are also congruent. We'll use our usual formula for the area of a right triangle. This first one will be BX times that radius. Here we have CY times the same radius. We can factor out RA. We can do this substitution again for BX and CY. So this length over here is just our side BC. And in the usual way, we'll let lowercase a be the length of side BC. So this is A times R sub A. So again, to find the area of triangle ABC, we'll find the area of the quadrilateral and subtract this pentagon. Our first area is this, S times RA. Our second area is A times RA, so we'll factor out RA. And we have an expression for the area of our triangle in terms of the radius of the X circle times the difference of the semi-perimeter and the length of the side that is tangent to that X circle. And there was nothing special about that particular side, so we can apply it to the X circles tangent at any of the 3 sides. For example, RB times S minus B. Let's return to problem 11. We're given information about the incircle of our triangle, so let's let R be the in radius of triangle ABC. And we'll let R sub A and R sub B be the radii of the X circles I'm calling A and B. In the usual way, we'll let lowercase a be the length of BC. So X circle A is going to be tangent to side BC. And because our triangle is isosceles, we'll let B be the length of AC and AB. AC will be the side that's tangent to X circle B. We'll be using our area formula, so let's write the area of our triangle. We'll call it K. In terms of the in radius, this is the semi-perimeter times R. We can also write the area of our triangle in the usual way, 1/2 A times the altitude drawn to side A. Let's draw our incircle here for a sec. Here's A, the side length of BC, and B, the side length of AC and AB. The height height of our triangle is AM, so we can use the Pythagorean theorem to solve for h. This is b squared minus the square of a over 2. Let's write an expression for the semi-perimeter in terms of a and b. We have two sides of length b, and we'll use this expression for r, the area of our triangle over the semi-perimeter, and we can substitute 1/2 AH for the area. We have that our three side lengths are integers, so our strategy here will be to pick a convenient value for a, and then if b ends up not being an integer, we'll multiply by some factor so that both a and b are integers. Let's summarize all of our equations. Scanning these equations here, we have a good shot at getting an integer if we let a equal to 2. So let's go ahead and substitute this into our four equations. This will be b squared minus 1. Here the 2's are going to cancel, and we have h over s. The semi-perimeter now is going to be b plus 1, which we can also substitute here into equation 2. From the fourth equation, substituting a equals 2, we get k equals h. We can also substitute that here. We also have our area formula from the excircles. We can replace this s with b plus 1 and replace this a with 2. This gives us the radius times b minus 1 for the area of our triangle. We can also compute the area of our triangle using the other excircle, and we'll substitute b plus 1. So here's another expression for the area of triangle ABC. Let's summarize all of these once again. First, I'll list all of the expressions for the area of our triangle, and we still have this relationship between h and b. Here we see that RB is equal to the height of our triangle ABC. Let's draw our circles without the triangle for right now. This will be the incircle of triangle ABC. It shares a center, according to the problem statement, with the circle omega. Then we have the excircle that's going to be tangent to side BC. From here we can find the radius of our circle omega. This is r, the in radius, and this is r the radius of this excircle. So this is going to be r plus 2ra. We also have that circle omega is tangent to the excircle b. So this excircle is going to be somewhere out here. So the distance from the in center to IB is going to be the radius of omega and the radius of that excircle, and we'll substitute. Now let's redraw excircle b and our triangle. It's going to be tangent to side AC, and we'll call that tangent point T. So here's our isosceles triangle, and it has a height of h. And recall from above, this height is the same length as the radius of our excircle. So let me extend side BC. This excircle is going to be tangent to this segment here, and its center is going to have the same height as this point A above this line. So we have a circle that comes around like this, and these are supposed to be the same height. If they're the same height, then we have right angles here, and you should be able to spot the congruent alternating interior angles in these two parallel lines. So once again, the angle formed by the center of this excircle A and M is 90 degrees, and angle IBAC is the same as angle ACM. Here's our tangent point T, so I'll just draw this radius. So we have a right angle here between AC and this line here, and we actually have these two triangles, AMC, with this angle marked in orange, and IB, the right angle here at T, and A again, with the same congruent angle. AM has length H. IB to T, that's the radius of this excircle, but we have actually that these two lengths are the same, so not only are they similar, they're also congruent. From this we can see that the distance from IB to A is the same as AC. That's part of this triangle. We're going to call this lowercase b. Now I'm going to draw this triangle once again, starting with its incircle and the concentric circle omega. Let's extend BC so that we can draw this excircle. Here's the center, the same height as A, and I'm going to join this in center with the center of this excircle, and since they're tangent, they're going to be collinear. So we have here right triangle formed by IB, A, and I. So we'll do the Pythagorean theorem here. That's our hypotenuse. We have from earlier that the distance from I to IB is this, so I'll substitute, squaring it on the left-hand side. The distance from A to IB is B, and the distance from A to I, that's going to be the height of our triangle minus this in radius. We're solving for the perimeter, so I want to keep the B and substitute as much as possible for these other variables. From earlier, we have that H is equal to RB, so let's do this substitution and solve for B squared. And instead instead of expanding these squares, I'm going to use the difference of squares factorization. So this is the first term plus the second term times the first term minus the second term. And we'll simplify. The r's disappear here, and here we lose the rb's. We can factor out 2 twice, and let's review all the expressions we have for the area of our triangle so we can remove some of these variables. Let's replace the r here with this fraction in terms of b. We can also replace rb with ra times b minus 1. So here's ra times b minus 1, and here we have b minus 1 over b plus 1 times ra plus the second ra. Now we'll simplify some more. Inside these parentheses, we're just left with ra times b. Here with a common denominator, we have ra times ra. I'll write that as ra squared. Here we have 2b over b plus 1. We have a couple of b's on the left and a couple on the right. Let's multiply both sides by this denominator as well. So that'll be b plus 1 over b squared on both sides of the equation. That leaves us with b plus 1 on the left-hand side, and then an 8 ra squared. We can combine this expression and that expression, so ra times b minus 1 is equal to h. Earlier we had an expression for h in terms of b. That's over here. H squared is b squared minus 1. To use that, let's take this and square both sides, and then we'll substitute b squared minus 1. Rewriting the numerator as the difference of squares factorization, we're going to get a b minus 1 that cancels. So the square of ra is b plus 1 over b minus 1. We can substitute that over here to get an expression entirely in terms of b. The left-hand side is b plus 1. The right-hand side is a times b plus 1 over b minus 1. We'll multiply both sides by b minus 1 over b plus 1. This gives us b is equal to 9, and happily, that's an integer. This was the result that we got when a was equal to 2. We can't get a smaller triangle this way, or else we won't have integers. So let's calculate the perimeter of our triangle ABC, and our answer is 20. If you'd like me to solve any other math contest problems, please leave them in the comments.